Okay, so now I'm going to give you the ideal gas law. It takes this form. PV is equal to nRT, and it really is a um, kind of a universal formula that connects physics with chemistry, and it's really, really important. Um, and it is the culmination of all the gas laws. It came after the other ones, but the other, Charles and Boyle's can all be derived from this. This one, if you're going to remember one gas law, remember PV is equal to nRT. Now what the symbols are, pressure, okay, so we're good with that. Pressure can come in different units, so you got to be careful. You can be in kilopascals, you can be in millimeters of mercury, or you can be in atmospheres. Either one of those is going to work, but I'm going to show you there's a little trick. Volume must be in liters. Now this is different than the other gas laws. The other gas laws you could be in millimeters and they'd solve out and it'd be just fine. With the ideal gas law, it's very specific that you're in the correct units because there's a constant, and I'll show you what happens there. So now this variable N, that's number of moles. And in all those other gas laws, we were always keeping the moles constant. We weren't changing the number of particles. Now we are. We can change the number of particles. T is temperature again. And that, like all temperature and gas laws, has to be in Kelvin. Okay? And then R is this new amount that is going to relate how a pressure times a volume is equal to number of moles times the temperature. It's kind of an interesting thing how that works. R is a constant, but it is dependent upon the pressure you're in. So if you're in kilopascals, R is going to equal 8.314. If you're in atmospheres, R is going to be equal to 0.081. All right? And millimeters of mercury, you can figure that one out, what R is going to be. But usually, millimeters of mercury, what you would want to do is, it's not very common, you put it into, you change the pressure into something more common and use it from there. So here's how a problem might look. All right? And I'll do one. So let's say I have this gas, and it's in a balloon. Okay, and the balloon has a volume equal to 2 liters. All right? And currently, the atmospheric pressure pushing on that balloon happens to be, not sure what, okay, there. The pressure, P1, or whatever, happens to be 1.1 atmosphere. Okay, we're somewhere down in Death Valley or something looking at this balloon. Now, one of the things about balloons is if the atmospheric pressure is 1.1 atmosphere pushing in on that balloon, then that's the same as the pressure that the balloon is exerting on the atmosphere. Otherwise, the balloon would change shape. So I know that the pressure on the outside of the balloon, just the way balloons work, is going to be the same as the inside of the balloon because that's the way it has to be. Okay, so I've got all these gas particles in there. And let's say it's kind of a hot day right now in Death Valley. And so T is going to be, what would be hot in Celsius? I don't know, 35 degrees Celsius. That might be really hot, but we'll find out, okay? And now, what I want to solve for is N. I want to find the number of moles that balloon has trapped inside of it. So I want to figure out how many of these little blue dots there are inside of that. So what I'm going to do, go back to ideal gas law. PV is equal to nRT. The pressure happens to be 1.1 atmosphere. Okay, the volume is going to be 2 liters. That is going to equal some number of moles in times R. Now, R in this case, since I'm in atmospheres, is 0.081. So I'm going to put that in there. Times R, which is 0.081. The units on it are atmosphere, liter, mole, Kelvin. Okay, that's what the units are. That Kelvin just reminds you that, boy, I had better change the temperature right there, that temperature into Kelvin. So it's going to be 35 degrees Celsius plus 273. And 35 plus 273 is going to work out to be 308 Kelvin. Oops. Change that. 308. So I'm going to put that down here. 308 Kelvin is my last factor. N then is going to be equal to 1.1 times 2 divided by 0.081. Divide that again by 308. And it's going to tell me that I have 0.088 moles of gas sitting in the balloon. So the number of little blue dots that I have sitting in there equates to 0.088 moles. Alright? So there's going to be a bunch of these. Whenever you have a problem that deals with moles and gas laws, you're going to be using that equation.